Welcome back to module 15 of the course Ultrafast Optics and Spectroscopy. We are continuing discussion on ab initio molecular dynamics, which could be used to study ultrafast processes in molecular system, particularly following electronic excitation. In the molecular dynamics, we can use three different approaches. One classical approach, which we haven't discussed. Another one is pure quantum mechanical approach, which we haven't discussed in this module. The discussion is in this module is based on only mixed quantum classical approach, where we move nuclei with the help of classical equation of motion, and we get the potential from electronic structure theory calculations. So, molecular dynamics is mixed with the electron structure theory calculations. So, in this approach, we have seen that the nuclei are represented by travelling Gaussian function, and so far whatever we have shown that these earlier derivations are explicitly shown for students who are relatively new to quantum mechanics. This is why we have dealt with one-dimensional problems so far. Now, we will go back to three-dimensional problem, where I have n number of atoms. Now, when we have, let us say, one-dimensional Gaussian, one can think of the classical position of the atom represented by this point in space. This is, let us say, R space, and it has a certain width. So, this is the representation of the travelling Gaussian, which is travelling in R space. Now, this is one-dimensional Gaussian. The moment we make it three-dimensional, it becomes, there is, let us say, another R1 and R2. There are, if we take it two-dimensional, then I have one Gaussian like this, another Gaussian should be like this. So, it makes a contour like this. So, it's more like localized in two-dimensional space. Similarly, three-dimensional space is another Gaussian which will be along the z-axis, R3 axis. So, and in order to get a localized function, because we have to localize the Gaussian, we cannot spread it over the space. In order to get the localized Gaussian function, we take the product of individual Gaussian functions. So, this is called trajectory basis function. We prepared this trajectory basis function. This is called trajectory basis function. We prepared this trajectory basis function by multiplying all the Gaussian functions. Now, how many Gaussian functions I should have? I have 3 degrees of freedom. Gaussian can move along x, along y, it can move along y, and it can move along z direction. So, 3 different directions it can move, and I have n number of atoms. So, total I have 3n number of Gaussian, one-dimensional Gaussian functions. So, this product is going to be rho equals 1, 2, 3n. So, 3n number of Gaussian functions I am multiplying and getting the trajectory basis function. Each Gaussian function we have represented, each Gaussian function is nothing but is represented by this, we do not have this multiplication sign here, this is just a Gaussian function. So, each Gaussian function is represented by its normalized Gaussian function. This is the normalization factor which we have seen already, and it has both R components. This is the Gaussian representation, and this is the propagation. It represents that it propagates along along the direction R, and R here representing the coordinate. It could be R1, it could be R2, it could be R3, R4, like this way. It's 3 n number of coordinates it's representing. So rho is the variable for that coordinate. And this form of Gaussian is now known. This is the particle form of the wave, and that's the way we get that. In earlier lectures we have seen how to get this kind of form. So what we have here is that I have trajectory basis function. I'm forming trajectory basis function by the product of 3n frozen traveling Gaussian functions, and then I have to finally represent the nuclear wave function, and nuclear wave function for a particular electronic state, ith state. So that nuclear wave function can be represented as summation of many such trajectory basis function. One can think about taking only one basis function, one trajectory basis function, and nothing wrong in it, but depending on what information we want to gather or what kind of dynamics we would like to explore, we might need to use many trajectory basis functions. So when we take many trajectory basis functions, clearly each trajectory basis function is representing one way of moving the overall system. Okay, and so let's say again I will reduce this problem to one dimension. Let's say this is one trajectory basis function. Again, trajectory basis function is a three-dimensional wave function, but I'll just, for simplicity, I'll take one-dimensional wave function. So let's say I have one trajectory basis function. This is trajectory basis function number 1, and another trajectory. So this is one way of reaction, one outcome. Each trajectory basis function has its own outcome. So so let's say one trajectory basis function is propagating along this way. This is the time axis. Another trajectory basis function is propagating like this way. There will be a phase difference between these two trajectory basis function. And whenever we have a propagating event, when we have a propagating event or time dependent event, then the relative position of each trajectory basis function with respect to the other has to be expressed, and that relative position in time is expressed by the phase factor. So definitely we have to use a phase factor always, time dependent phase factor, which is showing how individual trajectory basis functions are relatively related. And then because it is an summation of individual trajectory basis functions, I have to take the expansion coefficient as well for individual trajectory basis functions. So J is the trajectory basis functions, and depending on how many trajectory basis functions I would like to take, this number may change, this J number may change. So J is representing the trajectory basis functions. By this way we represent the total wave function, and the nuclear wave function on each electronic state is represented as a summation of multidimensional traveling frozen Gaussian basis functions with time dependent coefficients. Here index J labels multidimensional traveling frozen Gaussian basis functions on electronic state I. NIT, which we show it here, it should be actually N, then I, then T. So J is varying from 1 to NIT. NIT is a variable of time, is a function of time, because how many trajectory basis functions I need, that can be then controlled as a function of time. Whenever the right time will come in the dynamic simulation, one can introduce many trajectory basis function, and that's the basis of the ab initio multiple spawning method, where we can spawn or generate a new trajectory basis function as it is needed when the non-adiabatic coupling would be very high. We'll show you what does it mean very soon. So NIT shows the number of nuclear basis functions on electronic state I at time t. NIT is allowed to change during propagation. This gives birth to spawning, which will be discussed soon. The multidimensional traveling frozen Gaussian basis function is called trajectory basis function. Each trajectory basis function is expressed as a product of one-dimensional Gaussian basis functions. And we have seen what does it mean by this one-dimensional Gaussian basis function. Rho represents the 3n number of Cartesian coordinates of the molecule. And alpha, this alpha I rho j, this represents the time-dependent width of the respective Gaussian function. Then R bar jt, this one is representing the time dependent position. Then P, this one representing time dependent momentum, and gamma, this one is representing time dependent phase. And phase, it means whenever we get the phase, it means that I have multiple trajectory basis functions, and question is how different trajectory basis functions are internally related. Their relative propagation information is hidden in this phase factor. Now, in the previous slide, we have seen that these are the ways you can express the nuclear wave function. But in order to express the nuclear wave function, I have to depend on position, momentum, and phase. This information I have to give, and this information will come from the classical equation of motions. For an example, this R rho j bar t and P rho j t, they are propagated following Hamilton's equation of motion. These are classical propagator, and for this classical propagator one can write down these equations, and this equation is very simple to understand because we know that v, velocity, is nothing but p, momentum by mass, and v is nothing but derivative of the distance, which is dr dt equals p by m. So I get this equation. On the other hand, we know from the previously we have shown this Hamilton equation derivation for this propagation of the momentum. Propagation of the momentum will depend on this the gradient of the potential, and the potential is coming from electron structure theory calculation. So this is your quantum mechanical calculations from where we get the potential, we update the potential, and then take the first derivative with respect to the position, and then that negative of that derivative gives me the momentum propagator. And nuclear phase is propagated according to the integral of the Lagrangian. This integral of the Lagrangian will not show the derivation, but this is also coming from the equation of motion. The first term of the above equation, in this equation, in the phase propagator, the first term corresponds to the potential energy of the ith electronic state, and this m rho represents the mass of the rth degrees of freedom. Mass of rth degree of freedom. So, in M's module, this ab initio multiple spawning method, we are using classical propagator to propagate the nuclei. Finally, the multi-configurational nuclear wave function has the following form. We have already pointed out that we have to use Born expansion of the total wave function, and that is why the multidimensional form of the total wave function would be like this, where this is trajectory basis function and this is a trajectory basis function, and we do not have this. This is wrong. So, we have this trajectory basis function, corresponding electronic wave function, corresponding phase factor, and corresponding expansion coefficient. If we plug that in here in time dependent Schrodinger equation, then using the methodology which we have previously used, similar kind of methodology one can use. I am not explicitly showing here, but one can use similar kind of methodology and can get the matrix form of the of this coefficient. The Ci representing the coefficient matrix, Ci dot. And this also gives us the population. It is actually related to the population at the ith state. So, depending on the value of C dot, I will be able to get what is the population at the ith electronic state. Here I denotes the electronic state and features the ith electronic wave function. We note that the ith I here is actually depends on electronic coordinate and parametrically depend on nuclear coordinate. And this chi I is the time dependent nuclear wave function associated with the ith electronic state. As an unique nuclear wave function is associated with each electronic state, qualitatively different nuclear dynamics can be allowed on different electronic state. Once insert these expressions into time dependent Schrodinger equation, a set of coupled equations for the temporal evolution of the coefficients of the trajectory basis functions of each electronic state are obtained. So, basically this is nothing but d c j I t dt that is given here. So, this coefficient, time dependent coefficient we get in the matrix notation, we get this. Now, at t equals 0, all initial values of the coefficient and parameters which define the nuclear basis set, position, momentum and nuclear phase are provided randomly from the appropriate Wigner distribution, which features the combined distribution of the quantum particles coordinate and momentum in terms of the wave function. So, when we prepare the one trajectory basis function, let us say we are preparing one trajectory basis function in the upper electronic excited state. When you are preparing it, I need the initial position, momentum and phase information. That information will come from Wigner distribution. So, what does it mean by this Wigner distribution? Let us assume that I am in the ground vibrational state, V equals state, and ground vibrational state doesn't mean that its energy is 0, because we know that any molecule cannot be made vibrationless, because 0 point energy is a finite energy, is not a 0 energy. So, molecule will always be vibrating at the even at the 0 point energy level. Now, in the 0 point energy level, if we look at the wave function of the vibrational wave function, it represents a Gaussian function under harmonic oscillator approximation. This Gaussian function actually representing the spread of different configurations. So, basically instead when we think about electronic excitation, we say that this geometry are not equilibrium configuration, or equilibrium geometry is excited to the excited state. But in reality, that is not the case, because we can have many other such different configurations representing this spread of the vibrational wave function. So, I can have R1, I can have R2, I can have R3. Okay. So, many other configurations can contribute to the initial geometry, and that is why I have to what is the procedure for running this simulation is that you take different initial configurations and prepare your initial states, and then run those trajectories and then average them. We have to take the average of individual runs. So, this is done taking the initial configuration, different samples for the initial state is taken from the Wigner distribution. The Wigner function plays an important role in establishing the quantum to classical interface. During photoexcitation process, a single trajectory basis function can be placed on the excited state surface. One electronic state is populated with position and momentum obtained from Wigner distribution of the ground state. This trajectory basis function can be propagated on the excited state surface following Hamilton's equations, classical propagator. So, what we see that now I can again use Taylor series expansion and then use this as the propagator for the population, and we see that for this propagator what I need the derivative, because delta t is known. Delta t is the time step used in the molecular dynamics, ab initio molecular dynamics. So, that is known. Initial condition population is also known, that is represented by Ci. Ci is not directly representing population, it is actually Ci square modulus is actually population. So, it is related to population. So, we know that what is the coefficient value at t equals 0, and after time delta t, what would be the value of the coefficient, that depends on this derivative, and this derivative depends on this matrix elements, and these matrix elements are quantum mechanical effects, because it has a coupling term Hij term, and we know that Hij term exists when we are near the conical intersection or surface crossing regime. So, if you are away from surface crossing regime, this becomes almost 0. Okay. This is almost 0, and because this is 0, this propagation is nothing but a single surface propagation. So, this trajectory basis function, if I take one trajectory basis function, that will just propagate, and population will not change at all, population will remain constant. This population in the upper excited state will remain constant, because nothing can change the population without this this coupling vector, this coupling matrix. So, this propagation without Hij, this propagation is similar to propagation on a single surface in which Hij does not contribute to the complex expansion coefficient. Thus, population on the ith electronic state remains constant. Pi equals square modulus of this. This is the population in the excited state. However, during this propagation, at each time step we calculate the effective non-adiabatic coupling. Effective non-adiabatic coupling we calculate, and that non-adiabatic coupling I will show you what is the effective non-adiabatic coupling. This is represented by capital lambda I j. This is effective non-adiabatic coupling, which is nothing but modulus of this r dot d I j, where d I j is represented by this integral I r capital R j. This is the coupling vector. What I will show here is that this integral representing a very interesting coupling. J and I, they are electronic state, but this is the nuclear coordinate. What does it mean? It means that this coupling term is coupling two electronic states with the help of nuclear coordinate, and that is the non-adiabatic interstate coupling constant. So, we always calculate this effective non-adiabatic coupling constant, and if we see that this effective non-adiabatic coupling constant, if the value of the effective non-adiabatic coupling constant at a given time is larger than the predetermined threshold. So, let us say during these calculations I started the propagation from the FC point, which is Frank-Condon point, where the vertical excitation is going on. Then it is propagating. During the propagation, each time I will be calculating non-adiabatic coupling term, and if the non-adiabatic coupling term, here I am plotting each time how non-adiabatic coupling term is changing, it is going beyond a threshold value. I will set that threshold value is a predetermined threshold value, let us say lambda naught. This is lambda naught threshold value, and this is lambda I am plotting. So, if it is going beyond, consider larger than the predetermined threshold value lambda naught, it is considered that excited state trajectory has entered a region of significant non-adiabatic coupling. As pointed out earlier, Ames method adjusts the size of the total number of trajectory basis functions, aiming at describing quantum mechanical effects associated with electronic non-adiabaticity. A new trajectory basis function is spawned whenever the existing excited state trajectory passes through a region of significant electronic coupling to the lower electronic state. So, what does it mean? It means that the moment I have entered the spawning regime is defined by significant non-adiabatic coupling. Wherever it is present, it is called spawning regime, and whenever there is a possibility, whenever we see higher non-adiabatic coupling, then what we do, we spawn or generate a new trajectory basis function. So, now I have two trajectory basis functions, let us say. One trajectory basis function will be placed on the upper state, another trajectory basis function will be placed in the lower state. The spawning algorithm works in the following way. First, lambda naught parameter is defined to indicate entrance and exit coupling threshold values. Second, lambda ij effective is computed at each time step. When lambda ij effective exceeds lambda naught, this is labeled as T naught. Excited state trajectory basis function is propagated forward in time following Hamilton's equation of motion until lambda ij effective drops below lambda naught. This time is labeled as Tf. In predetermined number of basis functions is spawned within the time crossing time Tf minus T naught. In the simplest case, if only one trajectory basis function is spawned, a child trajectory basis function is created at the point of maximum non-adiabatic coupling. So, at this point, let us say of time, I will spawn one child trajectory basis function in the lower electronic state. because at this point the lambda ij effective, this is lambda ij effective, this value goes maximum, and that is why we do that. So, one can preserve the momentum and position when they are spawned. So, there are many methodologies one can use for the spawning mechanism, but this is nothing but or similar to stochastic Hopf or what is discussed in surface hopping method. So, what we have discussed so far is kind of a general idea of how spawning is done in ab initio multiple spawning dynamics, and we will continue this session in the next lecture.